Welcome back to another lesson with me, Mr. Wong. Today we're going to be looking at combustion reactions. Before we do so, let's have a look at the do now questions and have a go at completing them. In question 1 it says, write the equations for the following synthesis reactions between the following pairs of substance. Now, a synthesis reaction is where you combine two reactants to make one big substance. So if we have a look, synthesis reaction kind of occurs in a way like so. So it'd be A plus B, two smaller substances combining to make one bigger substance. So what we have here is sulfur plus oxygen. Don't forget oxygen comes as a diatomic pair. So it's SO or S plus SO2. And that gives us, combining them together gives us SO2. Okay? Sulfur would be solid, oxygen would be a gas, and sulfur dioxide would be a gas. Next one we have is phosphorus. And so phosphorus is P, chlorine is Cl. And we actually come up with a nice little thing where, again, chlorine comes in pairs, so it's Cl2. And so our formula looks something like this. So P plus Cl2 equals to PCl3. Now, some of you might be wondering, well, how do we know that this is PCl3? Think about it this way. It's not the direct method, but it can give you a little hint. So P, phosphorus, on your periodic table is 3 plus. Chlorine is 1 minus. If we remember our rules about valencies, if a compound has two opposite numbers, so numbers that aren't equal to each other, get rid of the signs, so get rid of the plus and the minus, and move the numbers to the direct opposite side. So 3 will come down to here where Cl is, and Cl, which is technically minus 1, will come down here, giving you PCl3. Okay? So there's that. So I have 3 Cl's here. Okay? I want to make it into a nice even number, so that's why I put the 2 here. Okay, so on this side I have in total 6 chlorine atoms. That's why the 3 is here, to make this into 6. And then P, because there's 2P here, so this is why the 2P is over here as well. The next one, we're looking at thermodecomposition. If you remember, decomposition is where you have a larger compound and it breaks apart into two simpler substances. Now, if I look at zinc as my example, zinc carbonate, and for those of you who are wondering what is the formula, zinc is 2 plus, carbonate is CO3 2 minus. So the signs are the same numbers, so 2 plus, 2 minus, same sign, so get rid of those numbers, combine the symbols together, you get zinc carbonate. Okay? This will make a metal oxide. So the only metal I have here is zinc. So this will become a zinc oxide plus, as you can see here, carbon dioxide here. So here we get that, okay? So zinc carbonate is a solid, zinc oxide would also still be a solid, and carbon dioxide here would be a gas. Phosphorus would be solid, chlorine, and so. And then we have copper hydroxide. Now, copper, you're not given the value for it, so you assume it's going to be copper 2 plus. And then you have hydroxide, which is OH minus 1. If you see here, one is 2 plus, one is 1 minus. So again, get rid of the plus and the minus signs and then swap over the numbers. So copper should be Cu bracket OH bracket 2. Okay? So this is what we end up with. Now some of you might be wondering, why do I use these brackets here? Remember, the brackets show you the compound. So if I wrote this H2O or OH2, okay, that's water, that's H2O. This is not equal to the same thing as saying this. Okay, this is water, bracket OH bracket 2. This is hydroxide. That's why we do the bracket in this case. And so the copper is the only metal we have that forms the copper oxide plus water in this case. So water in this case can be a gas, and so on with the oxides here. Okay, so what we're going to try and look at is a combustion reaction, this bit here. And just so that you can recall what we've done so far, we've looked at the conservation of atoms. So we've looked at the amount of atoms we have at the start. So if I have at the reactant, if I had 5 atoms, I still have as the end products 5 atoms. Okay, they might just be rearranged into a different kind of thing. And we've also talked about the possible indicators of chemical change. Okay, we've talked about synthesis. So an example of synthesis reaction is 2 smaller substances making into 1 big substance. And then decomposition is where you have 1 big substance and it breaks down into 2 small substances. Combustion, well, this has to do with oxygen gas. So if you want something to burn, it needs oxygen to power it. Okay, so here we go. We're going to look at some features of a combustion reaction. So some features here. If you want to look at your textbook reference, it's this bit here. And we're going to try and write some chemical equations along the way. All right, combustion reaction. We always associate combustion with burning and probably a flame. And for most part, you are right. So combustion is just about using oxygen to burn things to release a lot of energy. And obviously, if you have different colored salts, or you have different salts, you have different fires. One good thing we know that is actually fireworks. If you use fireworks, it also uses the same idea. So different color salts would yield different flame colors. And when you burn a salt, so as in fireworks, that's where all the different colors from fireworks come from. Another nice example here is the hydrogen balloon. So you react hydrogen gas with some form of oxygen and you get this really nice explosion. This is basically a very exaggerated version of the pop test, so where we try and test for hydrogen gas in some kind of substance. The next thing we're looking at is what is a combustion reaction? Now, to put it simply, a combustion reaction is where you combine oxygen. If you don't have any oxygen, you don't have combustion. And then the other thing is, whoops. Okay, so the other thing we know is in a chemical reaction, so that's starting here, a combustion reaction is exothermic. So it's exothermic, it's going to release energy at the end. Energy is going to be released at the end here. What does that essentially mean? It means at the start, some kind of metal or some kind of hydrocarbon reacts with oxygen. Okay? If it overcomes this energy gap, this bit here, what we call the activation energy, so the amount of energy required for a reaction to occur, so energy for reaction to occur, then we get a combustion reaction. And what we find is the energy of the reactants is greater than the energy or the final energy of the products. So when we form a combustion reaction, whatever end ingredients we get, okay, that has less energy than what we started with, and that's where we have a release of heat usually. It gives it as a minus, delta H. So there's 3 things you need to know for combustion reaction to occur. Firstly, you need some kind of starting ingredients to burn the fuel source. So you need some starting material. So you need reactant, an appropriate reactant. In some cases, we have metals. In some cases, we have hydrocarbons. Okay, hydrocarbons are basically fuel sources like petrol and all that. Very complex hydrocarbons. Next we have is oxygen for the fuel to burn in. So if there's oxygen O2 gas, we can cause a combustion reaction. Number three, energy to get started. So like I said here, we need some form of energy to cause this reaction to occur. If this energy is not fulfilled, then we won't be able to cause a chemical reaction or a combustion reaction in this case. So what we mean by here is to overcome the activation energy. So that's what we're trying to look for. Next is what type of reactions would we see with combustion. So if you have a metal and oxygen gas, you'll get a metal oxide. Okay, so if I have magnesium, burn it, expose it to oxygen, you'll get magnesium oxide. It's one of the examples we see a lot with the really bright light. If we burn a non-metal, so let's say nitrogen gas with oxygen, okay, we get some kind of non-metal oxide, and in this case, we get nitrogen oxide here. So nitrogen oxide. And then the other one we look at is a hydrocarbon. So a hydrocarbon is just made up of carbon and hydrogen. These X here, same thing with mass. These are just unknown values. So hydrocarbons come in a lot of different combinations. You might have butane, which is CH4. So that's, sorry, not butane, that's methane. And then you have things like CH, H6, and that would be ethane. So there's a lot of different combinations of these hydrocarbons out there. This is just one of those examples. You get oxygen, and then you get carbon dioxide plus water when these are mixed or formed together. This is a nice little diagram that portrays what happens in a combustion reaction. So you can see at the very top here, the oxygen gas, okay, comes towards our compound here, which is CH4. Again, this is methane. Okay, the oxygen gas comes in and latches on to the hydrogen atoms. Okay, so one oxygen latches onto the hydrogen atoms. Okay, and then the other oxygen will combine itself onto the carbon compound or carbon element. And so this is where you get methane plus oxygen, gives you carbon dioxide and water. However, we don't always necessarily have to form carbon dioxide, as many of you would know. This reaction is one of the issues where we talk about greenhouse gases, because carbon dioxide is a greenhouse gas. But that's not the only issue. If we don't have enough oxygen, so in this case we have a sufficient amount or excess oxygen, so we get carbon dioxide. If we don't have enough carbon dioxide, or if we don't have enough oxygen, we get a thing like this. Okay? This is called just carbon soot. And this is where we don't have enough oxygens to react with our fuel source. And it actually causes imperfect compounds. So instead of having carbon dioxide, you create things maybe like carbon monoxide, very toxic, or you may create carbon soot. And whenever you see any power plant create this effect where it's black, that's actually the color of carbon soot. So that's what you know it's an incomplete combustion. There's many other incomplete combustions that you see in the real world. You have the yellow flame. Now, if you remember, the yellow flame is created by having a closed nozzle. So it's not exposing to any air. So this actually causes us to have a limiting amount of air, okay? Or oxygen in this case. That's why we get the yellow flame. So it's not as efficient. So this is actually inefficient. So this is actually an inefficient burn. And if you've ever used glassware, uh, let's say we put a beaker on top of the yellow flame, if you expose it long enough, it actually forms a little black print on it, and that's the carbon soot we're talking about. So that incomplete flame, that limiting amount of oxygen, is actually creating a carbon soot layer onto the beaker, and that's not what we want. So that's why we use the blue flame. Not only is it hotter and more efficient, there is an excess amount of oxygen. But because we have excess oxygen, we should only be expecting to produce water and carbon dioxide. And so that's why we don't see any sooting on glassware if we burn it with a blue flame. Okay? Another thing we can talk about is the formation of carbon monoxide, highly toxic. Okay? The reason why it's so toxic is you can't see it, you can't smell it, you can't hear it, it can't be stopped. Or it can be stopped by a detector, but your usual senses won't be able to feel it. And carbon monoxide poisoning is very dangerous. So let's try and quote unquote look at all these reactions together: complete, incomplete, or insufficient and incomplete. So in hydrogen, or if we're looking at a complete combustion, we have carbon dioxide and water. This is the amount of energy that is released. So 892 kilojoules. This minus sign, so this minus sign just means energy released into the environment. Now, some of you might think, oh, how is energy released? That's actually released because of the formation of these chemical bonds. So by forming chemical bonds, energy actually gets released into the environment. Next one we have is an insufficient combustion reaction. So we might not have enough oxygen. See, we don't have enough oxygen molecules, and so we get carbon monoxide. We still form water, but we form carbon monoxide. So that's insufficient combustion. You can see that we release less energy in this. We also have an incomplete combustion. Oxygen is now a limiting reagent, okay? So you don't have enough oxygen, we form carbon soot, and that's where all the black carbon comes from. And it's a lot lower in energy compared to the insufficient. And the complete combustion. So you can see there's a big difference between the three here. The reason why the complete combustion has a greater energy release, obviously it's forming more chemical bonds, more complex chemical bonds. Okay, so this is what I was talking about. If you have the yellow flame, you have sooting on the beaker. If you had the blue flame, it's complete reaction or complete combustion, so you're forming carbon dioxide. Carbon dioxide doesn't have any distinct colors, so that's why you won't see any coating. Carbon soot, the solid carbon, does have a black coating on it, and that's why you see it so visibly after burning. Another thing we can look at is old steam engines. Now, this is one of my little favorite parts. If you ever looked at a steam engine or a steam train and it creates black smoke, now you know that's actually incomplete combustion. So you're not burning your fuel in the most efficient manner where you can get, firstly, the most amount of energy, okay, and also the least amount of toxic pollution. So if you have a dark smoke, then generally it's probably less energy efficient, but also it's probably more toxic, because carbon soot or carbon monoxide is really bad for you in terms of your breathing. It takes up the It occupies the space of where oxygen goes into your lungs, so you actually suffocate in that way. If you have light smoke, so probably if the out of the chimney it was coming out more like this light smoke here, now that's showing you it's a complete combustion. So fuel is being transformed more efficiently to heat and then to make carbon dioxide and water. If you have grey smoke, say probably this side over here, then it's probably a mixture of smoke and steam. So obviously that some of you might ask, why does it get lighter over time? That's probably because the soot particles in here, as the gas is expanding in all directions, the concentration of the carbon atoms is just spreading further apart. That's why it gets a bit more whiter in this image here. If we look at carbon monoxide poisoning, so let's look at some things. The most extreme case, unconsciousness, cardiorespiratory failure, so your heart, your lungs, death. The best way of looking at it is in cities, because in cities we drive a lot of cars. So a lot of cars, not all of them are 100% efficient. They will give out carbon monoxide. They might give off soot. They definitely give off other unhelpful gases. But that's not the point we're talking about here. We're talking about the combustion side of things. So the general concentration, parts per million, you have 7 parts per million being carbon monoxide. So in our atmosphere around large cities, 7 of those particles, 7 of those molecules, out of 1 million we look at, 7 of them is carbon monoxide. Now, to some people, that doesn't sound like a lot, but this is what we can look at. If you have 10, so you upgrade to 10, you're already experiencing drowsiness, dizziness, headaches. The actual threshold that causes death, 200, okay? And obviously, if you're closer to the engine of the car, you will take in more parts per million of carbon monoxide. Okay, let's look at this. So it says, question 1, fill in the table below to compare the properties of complete and incomplete combustions. What's the oxygen requirement for a complete combustion, incomplete combustion, and so on and so on? Let's have a look. Okay, so for a complete combustion to occur, you need excess amount of oxygen. Okay, for an incomplete combustion to occur, oxygen is the limiting reagent. We talked about what limiting reagents are. They're the things that prevent a greater yield of product. So what products do we get in a complete combustion? Carbon dioxide, liquid water. In an incomplete combustion, carbon monoxide, soot, carbon solid, and liquid water. What about the energy release? That's what we got from the slide prior. And this is a number we also got from another slide prior. So combustion releases more energy than incomplete combustion. That's also why engines want complete combustion. If you produce more energy, your car can be driven for longer per the amount of liters of fuel you put into your car. You do not want incomplete combustion, not just from an environment standpoint, but also as a consumer who wants to get the most out of your payments for the fuel. And then the next thing we're looking at is explain these kind of situations, so complete and incomplete. So a blacksmith uses a bellow to increase the temperature of burning coal. Now some of you might say, what is a bellow? Well, if you've ever seen any of those movies where the blacksmith is hammering away at a piece of metal, and then you have a little iron furnace with fire. The bellow is essentially a tool that they use to increase the oxygen intake. So where they go and press and introduce more oxygen. A fire in a caravan can often flare dangerously if the rescuer opens the door for the occupants. Okay, so we're going to try and explain each of these. The kerosene lamp has a thick black film, and then at the center of the haystack, um, for weeks you don't have any burning occurring. So we're going to have a look at these here. Okay, so let's have a look. So the bellow, its function is to increase the supply of oxygen gas. Why do we want to increase the amount of oxygen gas? Because that creates more combustion, and this will increase the temperature of the coal. Remember, the higher the temperature, the easier it is to bend the structure of metal. And then we have over here, fire in a caravan can be often dangerous. The reason being, and we can certainly show this, is if a fire is starting to die out and then all of a sudden you reintroduce oxygen into it, this is what we call a backdraft. So the sudden reintroduction of the oxygen into a small fire will actually cause it to burst into a bigger flame. So that's actually way more dangerous than if you just let it just burn away by itself. A kerosene lamp, so you might have to have searched this image up, but it's basically an old gas lamp, oil lamp, and the reason why it has a black film, it's because of the soot forming. So it was the incomplete combustion that was causing havoc here. If you have the center of a haystack can just stay there without burning, that's because if you make a really compact haystack and it was just burning on the outside, then there's not enough oxygen inside the hay to cause combustion. So that's also why you can get away with things in that concept. Let me just quickly show you, or I'll redirect you to the slow motion guys. But one of the videos they showed, which was really, really interesting and incredible, is this one with the backdrafting of oxygen. So what they had, so what you can see here is the lack of oxygen going through. When they reintroduce the oxygen, you'll see an incredible flame bursting out. See if I can just skip towards that scene. So they're just picking up, as you can see, it gets hotter and hotter. And then as soon as the firefighters try to reopen it, you can see a sudden burst of flame come back out. So there you have that to contend with. That's why it's very important as a firefighter, if a certain location has been closed off and the flame is running inside, you do not open the door again. Or at the very least, you do it with great caution, because it is very dangerous. Okay, let's try and check our knowledge and understanding. So identify the element always used during every combustion reaction. Well, we already talked about this. You always need oxygen gas. Name the compound produced by the combustion of aluminium. Remember, if it's a metal plus oxygen, you get a metal oxide. So we get aluminium oxide. Then C, it says the combustion in a plentiful supply of oxygen is called what type of combustion? If you have excess oxygen, then it is a complete combustion. Okay? Number 4, write the equation including the state symbols for the complete combustion of butane gas. Now, if you remember, butane is a hydrocarbon, so we said that a hydrocarbon plus oxygen is equal to carbon dioxide and water. We already know what the symbols for oxygen and carbon dioxide is, so that's not really an issue. So I'll just write these out, and then you can try and balance it in a second. So the hydrocarbon we have is butane gas plus oxygen plus carbon dioxide plus water. Now, part of the thing you need to know is the symbols. So all these are just that. Water is our liquid in this case. Methane is just a gas. Oxygen is just a gas. Okay, maybe we'll just do one balance equation to help you through this, and then you can do the other one by yourself. So if we look at the thing that's not balanced here, from what I can see, it's the oxygen and the hydrogen. Now, rule of thumb, we always try and solve for the symbol that only appears once. So you can see how hydrogen only appears once here. You can see also how carbon only appears once here as well. So what I'm going to try and do is I'm going to try and balance the carbon first, and then I'll work on my hydrogens, okay? So carbon 4 here, so carbon 4 there is done. Now I'm going to balance my nitrogen, so I have 5 in total, so I write 5 here, okay? So now according to this, my hydrogens and my carbons are all balanced. Let's compare my oxygens. I have 2 oxygens here. I have 5 oxygens, 2 more here, so 7 in total. Okay, so I have 7 oxygens in total. That number never works well with me because it is a very uncomfortable number. Just a non-number is very uncomfortable. So what I can do to cheat my way through this is I can times everything by 2. But before I do that, I have 7 oxygens in total. I know that 7 over 2 times 2, the 2 eliminates each other and I get 7 in total here. So I can write 7 over 2, O2. Now my equation is balanced because the 2 will cancel out this 2 here and I'll get 7 oxygens. But I don't really want to work with fractions. We're kind of told that we should try and put this in whole numbers. So what we can do is times everything by 2. So this becomes 2C4H10. This becomes 7 O2. This becomes 8 CO2. And this becomes 10 H2O. Now, we already balanced the equation before. We've just increased the number, so it's still balanced now here. And looking at number 5, that's the balance equation for ethane. And then we have petrol. Petrol uses octane, and so let's try and cover through octane here as well. Okay, so I already know what the equations look like. So in XX oxygen, I should get carbon dioxide and water. And so I can just balance it out. So this is now balanced here. Again, I want to get rid of the 2. And so this is what I get here. Remember, water in this case is liquid. I want to get rid of, and now in B, I have a limited amount of oxygen. So I'm going to get carbon monoxide. You could try this with carbon soot as well if you wanted to, and water. And so this is the value I get. Again, I want to get rid of the fraction. And so I get 2C8, H18 gas, 17, 16, 18 water. Okay, and so that's how we go about doing these calculations for combustion. And that's actually it for today's lesson. For combustion, just remember everything we've been doing about combustion is about what oxygen can do and interact with another element to cause it. So oxygen, so long as it's some type of metal plus oxygen, you'll get a metal oxide. If it's some kind of carbonate or hydrocarbon, you'll get carbon dioxide plus water, or you can get monoxide plus water, or you could even get solid carbon plus water. But these are the main combinations of combustion we're looking at here today. Anyhow, thank you for joining. My name's Mr. Wong. Thank you for listening and staying tuned. And take care.